Okay, well, I don't know if Wong's coming, but we did a lot of stuff last time. I don't know if you had a chance to watch the video, but I highly recommend it because this stuff is not really covered the same way in Griffiths. Now we're going to converge with Griffiths probably by Monday, but there's just a lot of terms that he really just mentions almost in passing as if you're already familiar with them. And so we're spending a little bit of time at the front of chapter 3 going through some terms and details, doing examples. So we talked about a vector space, which of course you're familiar with two-dimensional, three-dimensional vector spaces, but we are going to be using infinite dimensional vector spaces in quantum mechanics. We already have been, we just haven't been thinking of them that way. And a vector space means a collection of things, those things are called vectors, which is closed under finite linear combinations. So you can take any finite linear combination, it's still in your collection of stuff, then that thing is a vector space. It's got to have a bunch of other axioms satisfied too. So important for us is that the examples we did last, the most important ones are capital L2. That is the math symbol for the set of square integrable functions, the absolute value squared of the function integrated from minus infinity to infinity is finite. So the other name for that for us would be normalizable functions, right? If the integral is infinite or doesn't converge, we would even infinite integrals, we say they don't converge, then it's not in capital L2. We also said that, when we're representing states of a particle by a function like psi of x at time t equals 0, we also observed that if I expand that as an infinite sum of coefficients times, for example, definite energy states of the simple harmonic oscillator, those expansion coefficients are a sequence of numbers, right? We usually call them CNs. I don't have it written out here, but those CN expansion coefficients, if I tell you the CNs, you know how to reconstruct this. So those give me the same info. And that means one way of specifying a state is a square integrable function. Another way of specifying a state is a square summable sequence. And that means a sequence such that the sum for whatever index you're starting with, maybe for the harmonic oscillator, we started at 0, of the magnitude of Cn squared. Remember, each one of these represents a probability. If it's normalized, these would add up to 1, but it's got to be, something finite. If you haven't normalized it yet, it would be something finite. If you have normalized it, it would already be 1. Then those would represent probabilities, the individual terms. Okay, so that's another way of representing a vector space, and we did some examples on the worksheet last time. We'll do some more this time. And then more familiar, although we're not used to the complex numbers, two-dimensional complex vector spaces. That means your scalars are complex numbers instead of real numbers or three-dimensionals. We'll be using those later when we talk more about spin. We developed some notation for vectors, and we said instead of putting an arrow over something to represent a vector, we're going to put, instead of writing V like this, we're going to put whatever symbol represents our vector inside a line and an angle bracket. And it is kind of nice because it allows you, if you put a big messy expression under an arrow, it looks a little bit sloppy. But here, I can kind of put whatever I want in there. Remember, the symbol I put between the line and the angle bracket is really for my own convenience. It's to remind me what that vector means. When I say V, it doesn't really tell me much. But if I use the symbol psi at time t equals 0, that reminds me, oh yeah, it represents the state of a particle that maybe I gave a function for at time t equals 0. So here it is, written out the way we have been writing it. We said that was sort of biased towards x. Here's the unbiased way of saying it. That's like drawing an arrow on the board and saying, I didn't give you any basis components or anything like that. I'm just telling you it points in that direction. and it has a certain length rather than giving components. This is more like giving components, okay? So we could represent different vectors, even a function, right? If there's a square integrable function, I might label the corresponding abstract vector as just an f. So those are just to remind me what they're used for. Similarly, so I might say, here is a vector. I could give you its components relative to the x basis. That's kind of biased towards x. Or I could give you these expansion coefficients, and we're going to start thinking of those as the components with respect to the energy basis. It's easy to get x probability densities out of this. And if you give me this, if I want to know something about energy probabilities, I'd rather know this, because the magnitude of the Cn squareds are probabilities of getting a certain energy. So depends on what you want to know, which one's the most convenient. In finite dimensional vector spaces, I'm assuming you've seen column vectors representing vector components, right? So we just stack them up in columns like that. So we'll continue doing that in this course when we talk about spin. There is a similar way to view these two things, right? It's almost like this infinite collection of coefficients is an infinite column vector that just keeps going and going and going and going. It never ends. We never get to the bottom, right? Hopefully they're square summable, otherwise they wouldn't represent a physical state. If I give you a function of x, just like we were at the beginning of chapter 1 and chapter 2, we could think of those as a column vector. Just stack, so f of x, stack it up vertically and say the values are going as we go down in here. Now, for us, they're usually going to be complex values, but increasing x goes down there. 0 is somewhere in the middle. We're never really going to draw it out, but it's just notionally to show you all of them can be thought of as a column vector. When I give you this, I'm giving you a column vector if you want to think about it that way. If I'm giving you these numbers, I'm giving you a very long column vector. And here's the case you're used to in a two-dimensional vector space. They're always going to be complex numbers. Yeah, I'm going to try to repeat the same stuff several times. I mean, all this we talked kind of about yesterday, except for the column vector stuff. We also introduced the notion of an inner product, which means the same thing as a dot product. Tells you, just like from normal vectors, the degree of overlap between two vectors, W and V, is the inner product between W and V. That's sort of loosely speaking what it represents. So if, when someone gives you an abstract symbol representing a vector, you don't really know anything about it. It's just a symbol saying, I'm thinking of a vector and I'm calling it F. To get some real information, you always have to have the components with respect to some basis. So here, maybe I say, I'm going to give you vectors f and g by giving their components relative to x. How do we calculate the inner product between those two vectors that are sitting in an infinite dimensional vector space? We do this process right here, which really is the same process you've done before. Maybe I'm doing these in the wrong order because maybe I don't have the other one there, but oh, here we go. Let's do this one first. If you had, let's do it on the board. If you had two vectors in 2 dimensions, right? Let's call them v and w, right? And let's suppose, just for the sake of argument, that they're complex vectors, and I've given your components. So I say, here is a vector v. We'll denote it like this. It has components v1 and v2 relative to basis vectors e1 and e2. And here's another one, w. It has components with respect to the same basis of w1 and w2. And I'm imagining these are complex numbers. How do we calculate the inner product between v and w? Well, if you've ever dealt with matrices and column vectors before, you probably saw something about, well, the first vector, you put it like this, and the second one, you put it like this, and you just, go down the line, multiply them and add them. That's what we're going to do, right? So I would stack up my v's here, v1, v2, I write as a row vector, W I just leave as a column vector. It's in its sort of normal position, right? This one's sort of backwards, so I turn it into a row vector. And the other complication is because these are complex numbers, we're talking about a complex vector space. Whenever you turn it into a row vector, you have to put stars up there. So the formula, if you've ever seen this form before, I could write this as V1 star W1 plus V2 star W, should be a W2, which I could write compactly as the sum from 1 to 2 of Vn star Wn. That's a really complicated way of writing something that you know in a much simpler form, right? You just multiply like components and then add them, except here we need a star. Okay, let's go back to the slide now. So on an infinite dimensional vector space, say for example, where I've got on little L2, where I've really got an infinite number of components, I'm doing the same thing. Instead of going from 1 to 2, if I've got these components, C and Cn and Dn going from 1 to infinity, I just do it all the way out to infinity. And I hope that sum converges. If the Cn's and the Dn's represent a normalizable state, then this sum will converge. And this is the same thing too, right? This is sort of like saying, take the xth component of G, multiply it by the starred version of the xth component of F, and add them up. When you add things up in a continuous set, you just integrate instead of doing a discrete sum. So these are really the two different kind of versions of the same formula, for discrete, for continuous. All right. So that was the inner product. We defined the inner product, and that's the version we're always going to use in quantum mechanics. There are other ones you can define, but we're always going to stick to that. And then the norm is another name for the length of a vector, or the magnitude, or the absolute value of the vector. We're going to define that in terms of the inner product. So if somebody gives you a vector and they say, what's the norm of the vector? How much is it normalized or not normalized? What's the length of it? You just take the inner product with itself. That's the squared length, and then you take the square root. Okay, so that's the norm. So in quantum mechanics, we've got a vector space. We're going to define the inner product, which was on the previous slide. And now we're going to define the length of a vector as just the square root of the inner product of the vector with itself, which is what you've done before in finite dimensional vector spaces. Okay, we also last time, continuing my extended review here, we defined complete collections of vectors. So somebody could hand you, say, here we are, we're in a vector space. We're talking about maybe square summable sequence. That's how I'm going to represent my vectors. So the set of all square summable sequences, that's a discrete vector space, and I might say, inside those, maybe I could give you a collection of vectors, maybe just 5 of them, or maybe I give you an infinite but discrete collection, an infinite collection of vectors, but still they aren't a continuum. It's complete, that collection, if I can write any vector in my vector space as a linear combination of those. And it's the same way for a continuous collection. If I've got a continuous collection where that index k can go on a continuum of values, I have to be able to write any vector in the vector space as a linear combination of those, where linear combination here means instead of summing, I integrate because it's continuous. Okay. Then where we ended last time was talking about completeness of a vector space. You know, these are sort of like complementary concepts. If somebody gives you a collection of vectors and they say it's complete, you would know, oh, take any vector in the vector space and I can represent it in terms of them. A complete vector space kind of means something a little bit backwards from that. If you form any linear combination of vectors in the vector space with the right properties of the coefficients so that they're getting small fast enough, the infinite linear combination with those coefficients will reside in the vector space. This is something that you don't really, I'm not going to test you on it or anything, but it's just so that you've heard these words before if you go to graduate school and you start learning about this stuff. Or if you learn more math, you'll certainly hear about this. If you take real analysis, you'll hear about Cauchy sequences. What is a Cauchy sequence? Well, what we mean is, let's imagine we have a two-dimensional vector space. And instead of drawing vectors as arrows, so here's my two-dimensional vector space. Instead of saying, here's a vector, I'm going to represent that vector just by the point it would have landed on. So a point is a vector. It's just where it is relative to the origin, right? So a Cauchy sequence means any sequence that looks like it's converging to a point. So a Cauchy sequence, just very roughly speaking, would be something that this looks like it's a Cauchy sequence. I'm supposed to be drawing an infinite number of points there. It looks like it's getting closer and closer to a point. Or maybe something like this. They could just form a cluster, but that cluster has to get more and more concentrated in some region. So if I take an infinite sequence of vectors, they're really arrows ending on those points, but it's inconvenient to draw so many arrows. That's the notion of a Cauchy sequence. They have to be getting closer and closer together. To know what closer and closer together is, we need a distance on the space. How do you get the distance between vectors? We just take the difference between vectors with their tails at the same location and then take that norm of that. How big is the difference between the vectors? Okay, so I'm not going to go through the technical definition of the Cauchy sequence in terms of epsilons, but a complete vector space, a vector space V is complete if every Cauchy sequence of vectors converges to a vector in the space. And the example I think I ended with was here's a perfectly legitimate vector space. Suppose I say all points in the plane representing vectors, but I'm going to restrict it a little bit. I would say all points in the plane that have a rational x coordinate and a rational y coordinate only. That's going to be my vector space. And the scalars I'm going to be talking about are rational numbers. So we're going to be taking rational linear combinations of vectors with rational components. That's a perfectly legitimate vector space, but it's not a complete vector space because, I might say, here is the x coordinate of pi. Now, there's no vector that ends and has an x coordinate in pi in this vector space because it doesn't have rational components. But I can take a sequence of rational x components that get closer and closer to that just by taking rational approximations to pi. So you just do have to be careful. And this is really to reassure you. We went through this example of, there's something that seems, how could that not be complete? Continuous functions of x. It seems like it should be complete, but no, it's not complete because you can get sequences of continuous functions that get closer and closer to a discontinuous function, but I didn't allow those to be in my vector space. So that's not a complete vector space by itself. For us, the takeaway message is, oh, capital L2, little l2, they are complete. So we don't have to worry about it. If I write one of these infinite linear combinations, as long as the coefficients get small fast enough, I am going to end up with a vector that's still in that space. So we'll put all this together in just a second. Okay, so looking at that second worksheet, maybe we should do the first one together to make sure we're all on the same page. So this is the one where we did 1 through 6. It's got the integrals on the front, and now we're on the back side. We did 1 through 6, and we're on 7. The first part of 7 says, I think I've got it up here, give an example of a complete collection of vectors in little l2. So now you got to say, wait, what does a vector in little l2 look like? It's a what? It's not an infinite sum. Vectors in little l2 are square summable sequences. So you should be giving it an infinite sequence. It's an infinite sequence that is square summable. So if I add the square of all of the terms, it converges to some perfectly finite real number. It won't be complex because we're taking the absolute value squared. So what's an example of a square summable sequence? Well, something like this. How could I give a sequence? Maybe I'll just give an infinite collection inside parentheses, and at some point I'll put ellipses there because we'll get the idea, right? So certainly, you know, 1/2, 1/4, 1/8, 1/16, 1/2 to the n. You get the idea, is a square summable sequence. How do I, so this is an element, it's an infinite sequence of numbers. In this case, little l2 could have complex numbers, but I'm trying to keep it simple here. These are complex numbers, they just happen to be real complex numbers. The square of these would, so we're going to check out, is the sum, well, let's write out the sum of the squares of these. 1 plus 1/4 plus, that's the square of this, plus the square magnitude squared of this, 1/16, right? And so on. This can be written as the sum of 1/4 to the nth power, sum from n equals 0 to infinity. And that's a convergent geometric series. You could use your 1/1 minus x. This converges to 1/1 minus 1/4. So what we've shown is that this is an element of little l2. That's just one element. Now, we're supposed to be giving a complete collection of vectors. And that means that any element, any square summable sequence should be able to be written in terms of a linear combination with complex coefficients of the huge collection that you're going to give me. Here's just one. I mean, I can't just give one vector. That's not going to be a complete collection. I could only get multiples of this vector in that case. Those aren't the only square summable sequences. And they've all, every vector, you know, especially in this discrete case, should be an element of little l2 in this collection. So I left myself a lot of room here. It's still not a lot of room. I probably am have to give an infinite list of them, but hopefully I can do a pattern where we see it. Anybody have an idea of what might work? Certainly, if you think by analogy with 2 dimensions or 3 dimensions, right? If I said, here suppose we were in, well, okay, I'm giving it away, but that's what we're asked in C. What's an example of a complete collection of vectors in, I changed my mind here, this is supposed to be C3, a 3-dimensional complex vector space. Right, x hat, y hat, and z hat, or here we're going to call them E1, E2, E3, just so that we can generalize to more dimensions. If we were to write x hat, y hat, and z hat in terms of their x, y, z components, we would say x hat looks like this usually, right? Here, this is the unit vector. This is its x component, y component, z component. Here's y hat, and here's z hat. So the answer to C is, that's one. There are an infinite number of answers. That's just a particularly simple one I could give for question C, given an example of a complete collection of vectors in C3. What would, you know, so suppose I say in C3, let me just take a random vector in C3. Here's one. I'm going to give its components. -32 pi 7.1. How do I write that as a linear combination? I just made it up random. In fact, we'll put an I in there just to be sure. That's a pretty random element of C3. I should be able to write this as a linear combination of these three. What coefficient should I use in front of this one? -32, right? So this is -32, 100, plus pi, 010, plus 7.1i times 0, 0, 1. So that's kind of, in so many words, a proof that I could do it, right? I mean, I could put an A, B, C there, and then it would be a perfectly general proof. So what are we going to say for A? What's one example? There's a lot of other examples we give here that require us to be a little bit more creative to get the correct linear combinations. But what's the analogous thing I could do for little L2, where I've really not just got sequences with 3 elements, but infinite sequence? We just continue the pattern, right? I think I've got that. This is my solution scanned in here. So this is the easiest one to do, right? Here's certainly a square summable sequence, right? 1, and then followed by infinite zeros. And then 0, 1, followed by infinite zeros, and so on. Got the pattern. We only needed 3 of them to give the idea, so we got a lot of ellipses in there. And then, is it clear that I could write any square summable sequence, A, B, C, D, E, and so on? Yeah, same way we did here. We would just have, I probably wouldn't write it out longhand. I'd write it out with an infinite sum. That certainly is a complete collection. What if I add in another vector there? In other words, what if in this case, I say, okay, this is a complete collection. I proved it right here. What if I put in a 4th vector, 1, 1, 0? Is that going to mess up the fact that it's complete? It is redundant, so it seems a little bit inelegant, right? It's probably even messier than it was before, but I can still write any vector just in terms of these 3, and therefore I can write any vector I want in terms of those 4. I just don't even have to use the 4th one if I don't want to. So you don't mess anything up in terms of completeness, other than aesthetically, it's a little bit ugly when you add in extra ones. Completeness is no problem. There's no claim that it's minimal. Here's another example. 1, this one wouldn't be so convenient. 1, 1, 1, 1, 1, and so on. You agree those are all square summable sequences? Yeah, anything that terminates in an infinite number of zeros is going to be square summable. Here I would have to be a little bit more creative to write an arbitrary vector in terms of those, but I certainly could if I worked at it. That one's not redundant, right? That would be sort of like taking 1, 1, 1, and 1, 1, 1. They wouldn't be unit vectors, but there's no claim here that they have to be unit vectors. More questions on that one, or why don't you guys just take a minute? It's a little bit weird with only 2 people in here, but try to fill out B, and we'll give some other examples for C that aren't quite as convenient. Little L2 is square summable sequences. So an element is an infinite sequence of complex numbers. Capital L2 is a square integrable function. So they are complex functions, but any real function is complex, and it might be nice to have real ones in there. So you're going to be giving an infinite collection, probably, of square integrable functions, so that if somebody hands you a random square integrable function, you could write it as an infinite linear combination of that, guaranteed. And the hint is, you've already done it earlier in this course. You know how to do it several different ways. Well, not even that. Think of the simple harmonic oscillator. And the energy eigenfunctions. That's a nice, simple example, right? So I would say, let's just finish talking about it together. Here is my infinite collection. I'm going to be very brief. Psi n of x, okay, associated with the simple harmonic oscillator potential. Infinite collection. N goes from 0 to infinity. So I've got an infinite number of functions. They're certainly all square integrable functions. So they're elements of capital L2. I know there's a lot of pieces, but we're going to keep repeating and repeating and repeating until you start to know what to think of when I say capital L2. These are an infinite collection of things in capital L2. Now, if somebody gives you a random square integral function, could I write it as an infinite linear combination of those? Sure, we did that back in chapter 2. I should be unsharing the screen now. Well, I'll go back to that in just a second. Psi n of x. That was the statement that these do form a complete set. So we already know it, you know. So we could do that. And well, let me go back here away from the board because I've still got the screen shared. That's an easy example. So for capital L2 there, I'm using this. Ooh, that wasn't good. Come on. Guess I must have clicked on something. There we go. Okay, so for the simple harmonic oscillator, the claim was these are a complete collection. I guess we're not moving around enough in here. And if I took another potential, say instead of a quadratic potential, that was the simple harmonic oscillator. Suppose I take a quartic potential. That's going to give another infinite collection of energy eigenvalues or solutions that are normalizable, and I could use those ones as a different collection, right? So those are all different possibilities of complete collections of vectors. They don't have any extra ones in there either. You know, I could throw in extra ones. Oh, here, I guess I did do that. Suppose I take the union of these two sets, in other words, the collection consisting of all of them, the harmonic oscillator ones plus the ones associated with x to the fourth potential. Oh, that's going to be redundant, but that's okay. They're still complete. I could write them in terms of just this. So this all together, you know, technically still means complete. It means you're not missing any. Doesn't matter if you have too many, you're just not missing any. Okay. You know, here's, you know, if you want to make your life difficult, you could take harmonic oscillator, psi0 plus psi1, psi1 plus psi2, psi2 plus psi3. There's lots of ways you can combine them together and not miss anything. You know, that would be like x hat plus y hat plus z hat. That's a perfectly good basis for a three-dimensional vector space. It's not the most convenient one, but it works. I'm just trying to work through the definitions here. Oops, I'm not sure why that, oh, that disappeared because we're going to the third one, right? So there's the example we gave. Here's another example of a complete collection in C3. Oh, I threw a couple extras in there. I didn't need, you know, the first three alone would have been enough. That would be a complete collection, but I threw a couple of random bonus ones in there. Doesn't matter. They're still perfectly good. You know, a lot of times people would write them as column vectors, but those are sort of hard to type out and write out. So I wrote them as row vectors. Here's another, you know, if you want to be excessive, I could say, oh, my collection, you want a complete collection of vectors in C3? I'm going to give you all of C3. Well, it's definitely guaranteed that I can write any vector in C3 as a linear combination of vectors in C3. In fact, I only need one in my linear combination because I've already got all of them in the collection. A ridiculous example. But sometimes it's good to think of ridiculous examples like that. All right, any questions on 7 or other examples you want to talk about? All right, so that was complete collection of vectors. Those are allowed to have extras in it, even though we don't really like it. An orthonormal collection of vectors is not going to be allowed to have extra ones in it. So orthonormal collection of vectors means is a collection of vectors, not necessarily complete, but they all should be mutually orthogonal. In other words, their inner product is 0 between two different ones, and each individual vector in the collection should be normalized. Okay, they don't have to be complete, just, you know, I could be in an infinite dimensional vector space and I could give you a collection of just 2, an orthonormal set consisting of 2. We talked about orthonormality being written in terms of the Kronecker delta and the kind of usual discrete case, and we then defined Dirac orthonormal to mean this, and we saw a little bit of how that was useful. And we'll keep returning to that. You'll see Dirac orthonormal appear in chapter 3 in a very cursory fashion, but it's, it's a little bit confusing by how brief it is mentioned in Griffiths. All right. You guys meditate on problem 8 since we spent a lot of time together on problem 7. Think about doing problem 8, which asks about orthonormal collections of vectors in little L2, in capital L2. So you got to think about what vectors I'm writing down. What is a vector in little L2? What is a vector in capital L2? All right. Zach, why don't you help me out with what you're thinking on the first one, A in 8.
Well, I was thinking that seemed to be kind of similar to how we did 7A.
Uh-huh.
We'd have okay, so in each element, you're like doing like 1, 0, 0, not like.
Mm-hmm.
But if you're looking for a set that's not complete, not just like draw, we have to stop it there.
Yeah, I mean, we could say, we'll throw in one more just to be a little bit generous. And then, oh, that's it. There's just 2 vectors in there. They are normalized because the sum of the squares of all these from 1 to 0 to infinity is going to be 1. 1 plus 0 plus 0 plus 0 is 1. Same thing for this one. This one's normalized, so that's the norm or orthonormal and orthogonal. If we take the inner product between these, right? If I call this V and I call this W, right? V, W, then if we compute V inner product W, we better get 0. That's going to look like 1, 0, 0, 0, inner product with 0, 1, 0, 0, so on. And that's going to be 1 times 0, 0, 0 times 1 is 0, 0, 0, 0, 0, 0. That's 0. The inner product being 0 means they're orthogonal. So they're orthonormal, but they're not complete. We don't have nearly enough in there, right? We need an infinite collection to be complete. Good. What about, we could do a similar trick in B, of course. Psi 0 and psi 1, or psi 1, 0, psi 1, psi 2. We already know they're orthogonal to each other. We didn't prove that, and in general, it's going to be kind of tough to do all the integrals that would be required to show that they're actually orthogonal. You would need to say, remember our form for the simple harmonic oscillator energy eigenfunctions. We had something that was a polynomial times a Gaussian function. So they're kind of ugly, right? Psi 0 was a normalization constant. Don't force me to tell you what it is. Times e to the minus m omega over 2 h bar x squared. And psi 1 was, some other normalization constant times x times e to the minus m omega over 2 h bar x squared, and so on, right? They get uglier, bigger polynomials out in front as we go down. And what we're claiming is that if I use, this Dirac notation, suppose I say, I want to show that the inner product of the vector that is psi 0 with the vector that is psi 1. By definition, that means the integral from minus infinity to infinity of psi 0 star as a function of x, psi 1 as a function of x, dx. Okay, I could do that one, right? That's a Gaussian lookup one. The product of the two Gaussians is Gaussian. I got an x out in front. That was in my table of Gaussians. So we could do it, but it's going to get increasingly painful to show, for example, that psi 8 is orthogonal to psi 18 or something like that. I mean, it would just be a horrendous mess. It's not going to be so simple. And for more complicated potentials, it's going to be almost impossible. So, but the claim is, if you study partial differential equations, you can show that the collection of all eigenfunctions of the solutions to the time-independent Schrodinger equation with that are normalizable forms a complete set. A complete orthonormal collection. Sorry. Not necessarily normalized, but an orthogonal set that is complete. All right, so that was a similar kind of thing, right? So if I guess I dropped the ball on finishing this, but we were going to say, oh, just psi 1, psi 0, and psi 3. Those two are orthogonal to each other, and I'm assuming we're taking the normalized version, so they're an orthonormal set. They're not complete. And similarly for C3, that would be like 1, 0, 0 and 0, 0, 1. Still missing one. All right. Let's move on to the crux of this. Oops, clicking the wrong one there. Okay. All right. And then finally, putting these two concepts together, an orthonormal basis is one that is complete, but it doesn't have too many. And not only that, not only is it complete and it doesn't have too many, the individual vectors are mutually orthogonal to each other and normalized. So it's like the Cadillac of bases, orthonormal bases. Of course, we always work with these in physics, right? X hat, Y hat, Z hat are an orthonormal basis, or I hat, J hat, K hat. Everybody wants to do that. So we're just generalizing this idea now to infinite dimensional vector spaces. 9's not too hard to do. Give an example of an orthonormal basis in little L2. That's going to be our infinite collection of 1 followed by zeros, 0, 1 followed by zeros, 0, 0, 1 followed by zeros, and so on. That's one. There are other ones, but they wouldn't be as easy to specify in that basis. Capital L2, that's going to be my collection of all the simple harmonic oscillator energy eigenfunctions. Not missing any. They're all mutually orthogonal, and I'm imagining that we've bothered to normalize them. And then C3 would be our 1, 0, 0, 0, 1, 0, 0, 0, 1 is one example. There's an infinite number of examples. That's the most convenient one. Questions so far? All right, so let's put it all together. Yeah, I sort of cheated here and just said, hey, we already really did what we needed to up above. A Hilbert space puts all these nice features together, and we're going to find out that we've been talking about a Hilbert space the whole time. I'm not sure how to draw the symbol that's in Griffiths, but I drew some sort of, curvy script H thing. I don't remember exactly what it looks like in Griffiths, but that's how I write my fancy H. Hilbert space. Fundamentally, it's a vector space. Okay, so you got to start, it's a vector space, but it's got some additional properties. It's a vector space that has an inner product defined on it. It has a norm, and the norm is derived from the inner product in the way we've been doing, right? The norm just means the square root of the inner product of the vector with itself is the norm of that vector. And it's complete with respect to the distance derived from the norm. That means we think of the distance between two vectors as being the norm of the difference between the two vectors. And we'll talk in a second about why that's important to us. But here is the most important takeaway thing for us. Capital L2 and little l2, they're really two different ways of representing the same kind of states, right? Because giving the CNs and giving the psi of x's, they're two different ways of specifying the same function. They're Hilbert spaces. They really are two ways of representing the same Hilbert space. So we're talking about one Hilbert space. And all the vector spaces, finite dimensional ones that you're used to so far from other classes, are Hilbert spaces too. It's really, things can more easily go wrong in infinite dimensions. In finite dimensions, it's really hard to not talk about a Hilbert space. And we'll be using those explicitly later on to talk about spin, right? Spin up and spin down states will be specified in C2. Why do we care? As I said, the states are vectors. We're thinking of them as vectors. When we give psi as a function of x, we're really giving components of vectors in one particular biased basis sense, biased toward the x direction. The time-dependent Schrodinger equation describes how those vectors change with time. Okay, well, that only references the vector space part of it, but what about the rest of it? The inner product, the norm, and really the completeness is the key thing. We, to get the distance to define completeness, we needed a norm, which came from the inner product. So we need to have this key stuff. What is all that distance stuff getting us? It's telling us that things like this actually make sense, right? On a normal vector space, we're only guaranteed that we can take finite linear combinations and end up with something back in the vector space. On a Hilbert space, you can take infinite linear combinations as long as you're careful about it. The CNs have to be square summable, right? The coefficients in your infinite linear combination have to be square summable. And, we're assuming these are normalized or at least normalizable states that form an orthonormal basis. So infinite linear combinations make sense in a Hilbert space, and that's the takeaway message. We're not going to be playing with these definitions the whole semester, but I just wanted to put it in the bigger context of what we're talking about. Okay, so that was in other words. In other words, all the series that appear in quantum mechanics converge to vectors in the same Hilbert space. There are other series we could write down which don't converge, and we're just not going to write them down. In other words, not only is the Hilbert space closed under finite linear combinations, it's also closed under the most important varieties of infinite linear combinations. That's the point of having the Hilbert space, because a lot of things can go wrong, as you know, from calculus with infinite series. All right, so yes, little L2, capital L2, and all those finite ones are, I guess we already said that. The inner product, it doesn't matter as long as you satisfy those axioms for an inner product. The norm for a Hilbert space has to be derived from the inner product as the square root of the inner product of a vector with itself. So the assumption is, in math, you can define a norm that really is independent of the inner product and talk about vector spaces that have those as kind of two independent quantities. But for Hilbert space, I believe the norm is always derived from the inner product as the square root of the inner product of the vector with itself. And the distance is always defined using the norm. That kind of makes sense. I'm going to wait for Zach to get back because, 50% of the class just left. So it's okay. It'll be a mini break today. Okay, so we've been talking about vectors. And at least if you take a linear algebra course, or even in differential equations, you talk about matrices, which are one way of representing a linear operator on a finite dimensional vector space, right? I think in differential equations, you do at least like 2x2 matrices or something like that. And we're going to generalize that to different kinds of operators. So we've been using the word operator in here for these things with hats on top of them. And, most of the time, X hat for us so far, although we're going to find that's a biased representation of it, we've been representing it as, hey, if your vector is represented by a function of X, then, well, let me go to the board for a second. What does an operator in general mean? It means if you have a vector, the operator is something that usually turns a vector into another vector, right? So let's think about ways to do that, right? Of course, if I've got a vector that has components A and B, one way to turn it into another vector with components is, multiply it by a 2x2 matrix, and that will turn it into another 2-element vector. That's the way we're used to. And we'll talk about linear operators in a second. Another thing I could do is to say, I'm going to define an operator. I'll just call it O. And when it operates on this 2-element vector, what it does is gives back the sign of the element A there and B cubed down there. That's as an operator, that's a perfectly legitimate operator that we could define. Turns out this one is linear, and this one is what we would call a nonlinear operator. We're going to make that distinction shortly. Now, we've been talking about vectors as being square summable sequences or square integrable functions. Let's take the function case, right? Suppose if I've got an operator and my vectors look like this, and I want to do something to it so that gives me a different function back. Maybe even I could hope that if this is square integral, then this is square integrable too. That would be an operator on our Hilbert space. What kinds of things can I do to functions to turn it into another function? Well, one thing I could do, right? We had this x hat operator, which is said, what do you do? If I apply x hat to f of x, what function does it give? Oh, it just gives me that function with an x multiplied out in front. That's a new function. It's a different function, right? What about our p hat operator, px hat, operating on f of x? It's also an operator. It turns a vector into a vector, minus I h bar, and we just take the derivative of f of x, and that's another function of x. So it's an operator. Well, let's stick with those now. The definition that we're interested in is that both of these, and in fact, all the operators we're going to talk about are linear operators. A linear operator doesn't just turn a vector into a vector, it has to satisfy a certain property. So let's call our linear operator L hat. If L hat is a linear operator, what that means is when I apply L hat to a linear combination of two vectors, and I'll write it in the Dirac notation here, scalar A times V plus scalar B times W, it kind of, I say it, distributes over the linear combination. That means it distributes over the plus and it moves through the scalars. Okay? So that means that we would get A times L hat of V plus B times L hat of W. So it distributes in the usual way. Is it clear that this is a linear operator? Right? If I take X hat, which is just multiplication by X, multiplying AF plus BG, certainly I can distribute through, and I can move the X through the constant A and get that this is equal to A times X F of X plus B times X G of X. So I've just made a proof there that that's a linear operator. It satisfies this condition. It distributes over the linear combination. What about this derivative operator with the constant sign in front? Is it a linear operator? Do derivatives distribute over linear combinations of functions? They do, right? So if I, let me just erase that for a second, but let's say we want to apply this operator to A F of X plus B G of X. You know the property of derivatives, it moves right through, it can distribute over a plus sign and it moves right through the constant, so it has all the right properties, right? Our other operators were just ones that were formed out of this, like the kinetic energy operator, which is p hat squared over 2m plus, well, yeah, that's it for the kinetic energy. The total energy involves the v of x too, and that would depend on what potential we have sitting around. So those are linear operators. Let's go back to the slides and we'll stop in just a second. I'm just about out of time. But let me show a couple of pictures here. Okay. So if you take linear algebra, people will talk about linear operators called linear transformations. So a linear operator that takes a vector to a vector. In other words, any vector in a vector space gets mapped to a different vector. Here's a picture of that happening. I put the tails of both these vectors at the origin, which is, sort of a conventional way of drawing a vector. And here is a linear transformation. Well, I'm imagining it's just a transformation, but here I guess I'm assuming it's linear. It takes this vector into that vector, and it should be doing that for all the different vectors in the vector space. It's really hard to draw that. For the same reason I wanted to use points before to represent vectors, I could, instead of drawing the green vectors, just draw a dot and say this transformation, I'm telling you, it takes that dot in the 2D, vector space to that one. How could I do that for all the dots at the same time? Well, here's a particular way of drawing what a linear transformation does. I could say, well, here's the plane. I put a picture of Mona Lisa behind it. And what I'm going to do is apply this transformation to it, and I'm going to draw what happened. In other words, where if you look at, whoa, I'm going crazy here with this thing. If you look at where Mona Lisa's nose is, at that same, I'm going to draw the effect of this transformation by saying the point, which represents a vector, on the tip of her nose is going to be mapped to the place where her nose ends up in the altered picture over here. There it is, right? So that means that this point in the plane, which is a vector, gets mapped to this point in the plane, right? The same as here's one that's pointing to her cheek. It gets mapped to this other vector here, which is shown as the red vector over there. So it tells you where they all get mapped to. And the nice thing about this is that You know, we're used to in 2 dimensions or 3 dimensions, if you think of linear transformations as matrices, those again are a biased point of view. Those matrix elements that represent the transformation depend on the basis that you've chosen. But if you choose a different basis, we'll do a worksheet on this next time, you're going to get different matrix elements. But here in a picture, you know, I can't do this in infinite dimensions. I pretty much stuck in 2, but I'm showing kind of a basis independent picture of what's happening. In other words, I don't need to put any basis or axes on there at all. I could just show you this picture and that picture, and I'm saying that's where they go. As long as you know where the origin is in there, that's where they go to. So let's stop there because it's been just about an hour now, and we'll continue on Monday